welcome to my YouTube channel. Today I'm gonna analyze CPET Fast Ramp data, and especially I'm gonna talk about the Wasserman panel, VT1, VT2, VO2max, and heart rate max. First of all, I'm gonna show you the setup for the CPET. As you can see the picture on the right, this is me on the bike, and I put mask right here, and on the mask there is a flow sensor, and this sensor detects my VO2 and VCO2, and there is a turbine inside, and depends on how many rotations the turbine makes, it can detect my tidal volume, for example. And I'm gonna show you a video of the screen connected to this CPET mask or turbine. So this is a screen of CPET, and obviously at the beginning it's all blank, and as time goes by and starting exercise, the data show up and looks like this. And this 9 panel is called Wasserman 9 panel. The first panel is ventilation over time. Second panel is heart rate over time. The third panel is VO2 and VCO2 over time. Fourth panel is ventilation and VCO2. So there's no time component in fourth panel, and the same for fifth panel, but x-axis is VO2 and y-axis is VCO2. And the sixth panel is about the ratio between ventilation and VO2 and the ratio between ventilation and VCO2 over time. Then the seventh panel is about tidal volume and ventilation. And eighth panel is about REL, which is respiratory exchange ratio. Basically, it's the ratio between VCO2 and VO2 and over time. Then the ninth panel is about PTO2 and the PTCO2 over time. So PT means end tidal partial pressure, and the PTO2 is oxygen, and the PTCO2 is carbon dioxide. Come back to the presentation slide. So goal is to find VT1, VT2, VO2max, and HRmax. So VT1 is ventilation threshold 1, and VT2 is ventilation threshold 2. So basically, ventilation threshold 1 is the point where you compensate the lactate accumulation. So basically, as you increase intensity of exercise, you produce lactate by your energy metabolic system, and as you increase lactate accumulation, you increase acidity of blood by increasing hydrogen ion. Then you have two ways to remove the hydrogen ion. One is just metabolism, so that's one way, and second way is the buffering system. So at the point of VT1, the two systems which I explained are in line with lactate accumulation. So you're fine doing exercise for a long time and for long distance, for example. But like at the point of VT2, the system is overworking, so lactate accumulation increase further. Then the buffering system or compensation system cannot catch up with the accumulation any longer, so you cannot continue the exercise for a long time or for a long distance. So that's VT1 and VT2, and you can detect VT1, VT2 by using the Wasserman 9 plot. So what you have to look at is the point, the ratio between ventilation and VO2 increase, but still the ratio between ventilation and VCO2 decrease or constant, maybe around here. And you check the deflection point in panel number 5. So you take a look at panel number 6 and find the point, it increase, then you check the deflection point in panel number 5. So data is stored in CPET. So as you see the data point right here in time-wise, you can find the deflection point right here. Even there is no time component, you can find the deflection point, and I'm going to show you how to do that in a moment. And that's how you detect the VT1. And for VT2, you should find the point where the ratio between ventilation and the VCO2 increase linearly with the ratio between ventilation and the VO2. so maybe probably the point should be around here or maybe here, and you can check the diffraction point in panel number 5 or panel number 4. So panel number 4 is usually more obvious, or you can see the diffraction point of VT2 more clearly. So probably here or here, I have to make this figure bigger, but yeah, probably it's more obvious compared to panel number 5 in terms of detection of VT2. So you have to kind of switch around the panel between panel number 4, 4 and 6, and 5 and 6. And also you can check the VT1, the VT2 in panel number 3 also, but like usually you check the panel among like number 4, 5 and 6, and probably that's enough. And maybe you can check panel number 1 for the diffraction point. You probably increase the ventilation as you increase intensity of exercise. So anyway, I'm gonna show you how to detect the point in a moment, and also I'm gonna make a plot of this. This is bigger version of panel number 5. So as you can see, you see the diffraction point right here, which is VT1, and the second point, which is VT2. And I made a trend line from the starting point of exercise to VT1, and from VT1 to VT2, and from VT2 to the end of the exercise. Procedure: first of all, I'm gonna import the data, then I'm gonna plot the Wasserman 9 panel. After that, I'm gonna find the diffraction point based on the Wasserman 9 panel. Then based on the diffraction point, I'm gonna find the VT1 and VT2. Then I'm gonna plot the trend line. Then I'm gonna find the VO2max, and finally heart rate max. I'm gonna show you how to do those all procedures by using MATLAB, so let's go to MATLAB. Okay, MATLAB. So first of all, I'm gonna import the data, and let's take a look at the data. So this is raw data I exported from CPET. As you can see, there is 875 rows and 16 columns. Each row represents each data point, and each column represents each variable, like time, phase, walk rate, VO2 per kilogram, VCO2, VO2 per heart rate, ventilation over VO2, ventilation over VCO2, tidal volume, breath frequency, heart rate, and the stroke volume, and the estimation of VO2max, the cardiac output estimated from VO2max. And actually I don't know CI, but I'm not gonna use this one. Based on these variables, I'm gonna plot the Wasserman 9 panel. So this is the code. So pretty much I'm just gonna plot one panel by one panel. So first panel is about ventilation, and I didn't really specify the x-axis, but like each data point is just 1 second. So like I'm just gonna input the ventilation, and actually the time starts from 8 seconds, but I just want to plot the Wasserman 9 panel. It just should work without specifying the x-axis or like time axis. Then second panel, I just put heart rate right here. This is fourth panel, third panel, fifth panel, sixth panel, seventh, eighth, and I don't have variable for PTO2 and PTCO2, so I just stop right here with H plot. So I will show you the plot. So plot looks like this. This is exactly the same plot as you saw it on my presentation. Then the next step is find VT1 and the VT2. So as I said, I have to find the point where VO2 increases although the VCO2 stays the same on the sixth plot, and probably right here. And you can check the x-axis, which is 466 right now, and you check the data point 466, and do the same thing for the VT2. You're gonna find the increment point for the ratio between ventilation and the VCO2, and you're gonna make sure the increment from the point is linear with the increment of the ratio between ventilation and VO2. And the program here. And you check the x-axis again, and you check the point with panel number 5 and 6, and I already did it, so I already have the data point, which is 468 for the VT1 and 608 for the VT2. So this is just the panel. I just made it bigger. So this is panel number 6. So you can see the diffraction point better. Could be here, or maybe it could be here, and VT2 could be around here. Yeah. So you just check the x-axis, because x-axis is pretty much the data point. So you save the data point right for this time 605, and you put the data point right here for VT2, and here for VT1. I mean, you put twice right here for VO2 and the VCO2. And this is panel number 5 with candidate diffraction point. And as you can see, there's a marker here, and it looks like it's a diffraction point for VT1 and the VT2 right here. And you check the diffraction point for VT2 in panel number 4. Is it here? Yeah, maybe right here, or could be right here. But that's how you check the diffraction point of VT1 and VT2. And after you define the point or data point for VT1 and VT2, you can plot the trend line, and it's simple. So I just find the index or point of my subject started the exercise, and it should be somewhere around 234 data point, and I'm gonna find the linear model from where the subject started the exercise to candidate VT1, which is 468, and do the same thing for VO2, and this is actually VCO2, and do the same thing for the VO2. And the function called fit LM gonna create the linear model between this data point, which is VO2, and VCO2. And I'm gonna save the model data into a variable called model VT1, just like this. Then I'm gonna create x-axis. So the data point or x-axis starts from EX, or like where the subject started the exercise, and ends with the data point, which is 468. Then I'm gonna create a number of data points between where the subject started exercise to candidate VT1. So the function called linspace creates whatever data points I desired. So let's say I put 1 here and 10 here, and I put 5 here in the third argument. I'm gonna create the sequence of the number from 1 to 10, but I'm just gonna create 5 data points. So linspace function can create the sequence, and you can customize where the number starts and where it ends, and how many data points you need. So basically that's what this function does. And I'm gonna save the sequence of the data here. Then based on the sequence, I'm gonna predict the value by using linear model. So basically this is x-axis, and I'm gonna find what y-axis in the linear model I defined in this code right here. And I'm gonna have all predicted data points in this variable called spread VT1. And pretty much I'm gonna do the same thing for the VT2. So I'm gonna put the data point, the first data point from VT1 to VT2, and do the same thing for VCO2. And again, I'm gonna create the sequence of the number by using the function called linspace. And of course, I'm gonna start the number from VT1 to VT2 and create this number of data points, which is 608 minus 469. Pretty much the number between VT1 and VT2. And this one become the x-axis. Then again, I'm gonna use predict function to predict y-axis based on the x-axis I just created in here. Then I'm gonna do the same thing again from VT2 to the max VO2 value. Then I'm just gonna plot all values in the plot. So I'm gonna run this. And you see this plot, this is panel number 5, and I just created the linear model, which is here from where exercise started to VT1, and from VT1 to VT2, and from VT2 to the end of the exercise. So pretty much there is a diffraction point right here and right here, and you can see the slope increases from the first model to second model, and from second model to the third model. So yeah, I agree with this is VT1 and this is VT2, and that's a trend line part. Then I'm gonna find the VO2max. So I already have VO2max data in raw data right here. So you just need to find the max value for the VO2max. But like if you only have VO2 data and you want to find out VO2max, this is the formula. You're gonna find the maximum value of VO2 during the exercise. The unit should be liter per minute with this. Then I'm gonna convert liter to milliliter by multiplying with 1000 and divide the value with my body weight. So that's VO2max, and the unit is milliliter per minute per kilogram. Then this is the prediction of my VO2max based on my age and workload, and this is another prediction by Wasserman and based on my age. If you only have limited data, this is the option you can predict your VO2max. So I'm gonna run this and let's see. So my VO2max is around 45, and my predicted VO2max is around 41 based on the Wasserman method, and another method is around 53. So Wasserman method actually underestimate my VO2max, but like another method overestimate my VO2max. If you don't have the CPET data, this is the way you can predict your VO2max. And heart rate max, obviously you just need to find the maximum value of the heart rate during the exercise, and you can predict your heart rate max as well. So by Fox formula, you can predict your heart rate max, subtract your age in year from 220. And Tanaka formula is, kind of same. You just subtract whatever 0.7 times your age in year from 208. And Nicolaides method is same. You just use your age and subtract whatever value of 1.44 times your age in year from 223. So I'm gonna run this and we can compare. So my actual heart rate max is 172. So that's I think the most reliable data because it's from CPET and I use the heart rate monitor. So 172, and based on Fock method 194, and based on Tanaka 180 or 190, based on Nicolaides method 185. So all of predicted heart rate max overestimated my actual heart rate max. So you can check your heart rate max by using heart rate monitor, and it's not really expensive. It should be available around you maybe, or simply you do maximum exercise and you check your pulse, and yeah. But before the exercise, that's how you can estimate your heart rate max by using age. And also you can find heart rate at VT1 and VT2. So based on this heart rate value, which is right here, 134 is my heart rate at VT1, and 160 is the heart rate at VT2. So based on this value, I can customize my training. For example, maybe if you want to increase your aerobic capacity, you can conduct your exercise around heart rate 160. And if you're tired, maybe you want to recover but you want to exercise, maybe you can do the training with this heart rate or just below this heart rate, and you can do like long slow distance LSD, for example. So that's how you can use this heart rate. But again, this is fast ramp test, so probably there's a delay between your metabolism and workload intensity increment. So obviously workload increase faster than my metabolism, and sometimes metabolism cannot catch up with the increment of work rate. So maybe the data is a little bit overestimated, so that's a concern. But the point of fast ramp test is to find VO2max. In contrast, in slow ramp test, you cannot really find reliable VO2max because as you exercise for a long time, you accumulate fatigue, and maybe your VO2max is underestimated. So fast ramp is fast enough to increase intensity, so you can remove the bias of fatigue accumulation, so you can have reliable VO2max in fast ramp test. So that's it. Thank you for watching my video, and maybe next time I can show you how to analyze the slow ramp test of CPET. So see you next time.